quick recap about vectors, so we can then look at this idea of projectile motion with vectors. There's a vector, I've called it u, it joins up to the point xy. There are different ways we can talk about the vector. I could write it as OP with an arrow indicating the direction, that's our position vector. We could write it as an ordered pair, probably least common of them all because it can be dangerous doing it that way. Column vector's a bit better, where we write it that way. And of course we could break it up into its actual component form. So x in the I direction plus y in the j direction. So different ways we saw vectors. The magnitude of the vector, basically the distance, so square root of x squared plus y squared, and the direction, which would be the angle it makes with the positive side, so theta, and we could work that out, inverse tan of y on x. Now I'm going to talk about these things called space curves. So everything we've looked at so far has been a straight line, so it's made life nice and easy. Now we're going to have this position vector, I'm going to call it RT, it's some function of the scalar t, so t is the parameter, if you like, that we would substitute into this thing. So there it is, there's one of them anyway, so we'll start off like that. As t changes, this vector obviously is going to change, because it'll go to different positions, and it will end up describing, so that endpoint would describe a curve. So it might move over here. So t plus, we've now added some small amount. We're now ending up at q. Its position vector would be OQ. And then it might move over there. So a little bit more t we're adding on. And so position vector is OR. It might look something like this. That might be the curve we're talking about. You know, all of those position vectors would lie on that particular curve. But that's what we call a space curve. Just a fancy name for a curve, I suppose. Yeah. Now, if we want to find the velocity at any of those points, then we would find the tangent to the space curve. So at P, the velocity would be going in that direction, because there's where our tangent is. Now, to find velocity and acceleration, no different to the linear motion, we differentiate whatever the components are. A lot easier. We break it into horizontal and vertical. We're back to straight line motion. You just differentiate each of those. All right. The displacement now becomes this. We'll have a displacement in the I direction, or the horizontal direction, which conveniently we'll call xt. Some function involving x, and we substitute t into it. And similar for the j direction. Velocity, then we would go and differentiate. So we'd differentiate the x function, we'd differentiate the y function. And the magnitude of the vector would be the square root of the components squared. So that would find us the actual size of the velocity. The direction it's travelling in would be the direction of that tangent, but we would work it out, we could say the inverse tan of the y component and the x component of the velocity. Acceleration, differentiate again. Magnitude of the acceleration would be, again, square the individual components. You'll notice I haven't worried about direction there. Yeah? Because if you want to know the direction the thing is moving, it's always velocity that you work with, because the velocity is telling you the direction that it's travelling in. Alright, so let's look at this one then. Particle moves, its velocity and time is given by this particular expression, so governed by a couple of trig functions. We're given the initial condition. So what they're telling us, this position vector, when it starts, it will be at the position, 1i. So it's on the horizontal axis at 1. Find the position vector of the particle at any time t, because they've given me velocity. Okay, we would need to integrate to get back. So what do we know? If I just look at the x component, I think it's just easier to break it up straight away and go, okay, here's the x component, it's minus 2 sine 2t. Separate my variables, so the integral of dx, and I'm going from 1 to x is what I want to find out. Negative 2 I can factorise out, sine 2t, 0 to t, and we end up with, after substituting in, there it is, so x is cos of 2t. Now let's have a look at the y component. That's a little bit easier because the y one's starting at 0, 0, time equals 0. The y component was also 0. So on the left hand side it's just y, So we get 2 sine 2t. So therefore, and I've written it in component form, but again, you could write it as a column vector. They're probably the 2 ways we tend to do it. They're the most common, either as a column vector or a component form. So cos 2t in the I direction and 2 sine 2t in the j direction. Second example, we've got 2 particles going here. And we have the position vectors for both of these particles. We want to prove that they will collide while travelling at the same speed, but also at right angles to each other. So we have to think about, what does this mean? Well, if they collide, they must occupy the same position at the same time. I mean, it's possible they could occupy the same position at different times, but that doesn't mean they're going to collide. So it's got to be the same time as well. So their x component will be the same, and their y component will be the same as well. Well, I've just looked at the x component here. T cubed minus 9t plus 8 is 2 minus 2t squared. I've ended up with this cubic to solve, which I don't like. Too hard. So maybe it was smarter to look at the y component. So t squared is 3t minus 2. Yeah, that's a lot easier to solve. Now I'm going to have to check, I guess, to make sure it does solve the other one as well, but this will give me possibilities. Now I have to find the possibility that works for both of them, I guess. So it's either going to be at t equals 1 or t equals 2. Sub it into the other one. When t equals 1, I get negative 1, so it can't be that one. Good. Sub it into the other one, I do get 0. So yeah, they will collide after 2 seconds. So we know that. So we've proven they do collide, but it's got to be at the same speed and at right angles to each other. So we've got to find our velocity. Well, differentiate each of them individually. So there's differentiating motion of A, differentiating the motion of B. Now when t equals 2, there's our 2 motions. One gives me 3i plus 4j, the other gives me minus 4a plus 3j. And then you look at it and think, well, hang on, they're different. But remember, it said the same speed. It did not say the same velocity. The magnitude of the first one's 5, the magnitude of the second one's 5 as well. So yes, when they collide, they will be travelling at the same speed. Okay, but there was one more thing. We had to prove they are at right angles to each other. So the direction, it's the vector for velocity that we would use, because that tells us the direction. Their dot product should be 0. That's how we prove vectors are perpendicular to each other. And when we work that one out, sure enough, we do get 0. So yes, that's the final part of the problem. We have now proven they do collide at right angles to each other as well. So that's just motion in general. Projectile motion is what we're really interested in. So, first of all, extension 1. We've got to look at that sort of motion first before we move on to extension 2. So extension 1, we move from advanced just look at straight line motion, that's all. So now in extension 1 we can look at 2-dimensional stuff. So it's projected into air, subject to gravity only. In 3-unit air resistance, it's so negligible we just don't worry about it, at least in the problems we look at. So we don't worry about any resisted motion. Resisted motion, extension 2, we'll handle it there. Which means we will start off with this. The acceleration in the horizontal direction will be 0, and in the vertical direction will be minus g. Because once that particle's in free air with nothing else happening to it, no air resistance, the only thing acting on it is gravity, and that's purely a vertical force. So there's nothing happening horizontally. Some initial conditions. Well, it will change depending on the problem, but when t equals 0, I'm going to say it's going to be projected with a particular velocity, whatever it is, v, and it will make some angle with the horizontal. I will assume that that starting point is the origin. So if they don't tell me otherwise, then yeah, it's not a bad idea. Let's start it as the origin, because all our position vectors are referred to back to the origin. Makes life easy. Okay, so there's my vector going off at this angle. It's going to have these components then of a horizontal velocity and a vertical velocity, which x dot and y dot we'll call them. So to find those initial conditions, just a bit of trig, we end up with v cos theta in the horizontal direction, v sine theta in the vertical direction. So at any point it will have this. So let's say we're at this point here where the angle now is alpha, and then it might move to, it gets to the top of the projectile motion that's purely horizontal. So the angle is 0, but then at some point it will now start falling. And that angle alpha, maybe I should have called it a different pronumeral, but anyway, it doesn't matter. Let's move on. As I say, for convenience, I've set it starting at 0, 0. You might end up with a problem where you're projecting from the top of a cliff. Those sort of ones are really common. You might set y at whatever the height of the cliff is. So that way you remember, oh, when it hits the ground, you're still saying y is 0. Because if you set the top of the cliff at 0, then when it hits the ground, will have to be negative whatever the height of the cliff is. Easy to make a mistake. Okay. So some notes: the maximum range of the particle will always happen, well, certainly when we're ignoring air resistance, when theta is 45 degrees. Right, 45 degrees. And that is, of course, to do with the actual trig curve itself. Well, when we work out the range formula, we can see quite clearly why that happens. So let's create the equations of motion that should help us solve any problem. We'll start with those acceleration ones. These are the things we know will always be true. And I've made life a little bit easier for ourselves to make gravity -10. The problem should tell you what to take. Sometimes you just leave it as g. I've written it as dx dot to t and dy dot to t because I'm going to separate the variables, and that's a lot easier. So we're going to integrate dx dot, and then answer has to be 0. So we end up with x dot is v cos theta. It's constant. It makes sense. If there's no forces acting on it horizontally, then the horizontal velocity is not going to change. It should always be v cos theta. Over in the y though, we get something different. There's what I was just talking about before. We've got this extra component there of -10t. That's basically gravity coming into play. So as time moves on, its velocity is decreasing. Okay, so there is an expression for our velocity vector. Magnitude of velocity would be the coefficient of these things. Integrate, again, let's get some displacement equations. Now we get vt cos theta because I'm conveniently starting at the origin. And the other one, y, we get vt sine theta minus 5t squared. And there's my vector for displacement or position. Okay. Common questions that you see in these problems all the time. When does the particle hit the ground? So you just think about it logically. Well, when it hits the ground, it's got to be when the y component is equal to 0. If I've set the ground at 0, of course, be careful with that one. What's the range of the particle? How far does it go? So now we're talking about horizontally. So we've got to find out when it hits the ground first. So when we find it hits the ground, we can substitute that back in and we'll find how far it went. What's the greatest height? How high up does it go? And again, if you think about the problem, what happens when it reaches the top? It's got to stop because it goes up, then comes back down. So it must be when the velocity in the vertical direction is 0. That's what we want to find. And when we do that, we can substitute that into the y component, and that'll tell us how high up it's gone. What angle does the particle make with the ground? Now, if you've projected from the ground, that question's real easy because it's a parabola, it's symmetric. So the angle that it takes off has got to be the angle that it lands with as well. Right? Sure, in opposite directions, but no. It's got to be the same. But if it's at any other points, well, of course you can't do it that way. So how do you find it? Well, find when in this case y equals 0, but whatever the point is we're talking about, substitute into the y dot, and notice I haven't bothered substituting into the x dot because that's constant. But then we just draw a triangle. Oh yeah, look, tan theta will be y dot on x dot. Work it out what it is. So, in summary, projectile motion, all we know about it, the only thing we have to worry about are those two things. So we know the acceleration horizontally, we know the acceleration vertically. Initial conditions. It is okay to quote those. So v cos theta, v sine theta. Don't really need to work them out each time. If the problem's a little bit of a variation, you might want to just double check and make sure, but yeah. Okay, let us do an example then. We're going to throw a ball, initial velocity 25 meters per second. The angle is the inverse tan of 3/4, so I get a nice exact value there rather than having an angle. Determine the greatest height obtained. Well, what are my initial conditions? There's my triangle. You'll see why I picked inverse tan of 3/4, because I get the lovely 3, 4, 5 triangle there. X dot's v cos theta, so 20 meters per second. And in the other direction, 15 meters per second. It's so much nicer when there are numbers, so you're not carrying over all these, pronumerals and what have you. You just got numbers you're working with. So I go through the process. This is what I start with. Therefore, I'll integrate, but this time I'm going from 20. So beautiful. Horizontally, we got 20. In the y direction, 15 minus 10t. No, you can't just quote those ones. You've got to derive them. A lot of times they might give you them. Brilliant. If they give it to me, fantastic. Now let's work out my displacement ones. Okay, 20t for dx to t. 20t for x. And in the y direction, 15t minus 5t squared. I should now be able to solve any problem they give me. I've got all the equations of motions I need. Remember, you're producing a solution for someone else. They need to know. There's a lot of working out here. They want to know what you're doing and why you're doing it. Okay, I'm now going to attempt to find the greatest height. I know it occurs when velocity in the vertical direction is 0. That's 3 on 2. Okay, 1.5 seconds. So when that happens, sub it into y, I get 45 on 4. Okay, greatest height is 11.25 meters above the ground. Range, how far did it go? Well, time of flight. I don't have to do a lot of calculations here because I know it's a symmetric problem. So if it took 1.5 seconds to go up, I'm going to take 1.5 seconds. So time of flight is 3 seconds. Sub that in, I just get 60, I've got my range. Notice I've said after half a second for this problem, so it's not when it hits the ground. We're going to have to work out some stuff here for velocity and direction. So horizontally, well, that's constant, it's 20. Vertically, it's 10. So 20, 10, hypotenuse is 10 root 5, tan theta is 1/2, the angle is 26.34, there we go. So after half a second, I know it's travelling at 10 root 5 meters per second and an approximate angle of 26 degrees 34 to the horizontal. To finish off with, let's have a look at last year's HSC question. They added a little bit of an interesting twist to this one. So we have a video game designer creating this game. They've got an obstacle that they're developing. The player has to reach one side of this pit they've got there. They've got to shoot a projectile to hit a target on the other side of the pit and able to cross. However, the instant the player shoots, the target moves. So the target, what it's hitting is actually moving as well. It's at a constant speed though, it's half the initial speed of the projectile. They've given us some initial conditions, not numbers, just letters, but that makes sense because they can then generalize it to any problem that they want. G, we're just going to use G. The only launch Nagel, typo, is the only parameter that can be changed. So everything else, once it's been determined, is fixed. They gave us these. We did not have to go and derive them. Thanks very much. That makes life a little bit easier. So taking the position of the player when the projectile is launched as the origin, again, makes life easier. Then we have a displacement one for the projectile, but also for the target as well, because remember the target is moving. Show that for the player to have a chance of hitting the target, D must be less than 37% of the maximum possible range of the projectile. So this was not a question that was one of those scaffolded questions where part I go and do this, part 2. Nope, you had to do the whole thing. There's the problem, now come up with a solution. What do I want to know? Projectile hits the ground, that's going to be something handy because that's when it's going to hit the target. So that'd be when y is equal to 0. So at that point I still don't know what the horizontal one is, so it'll be 2ut cos theta. I don't know what t is at that time yet. But that tells me then that 2ut sine theta minus a half gt squared must equal 0. There's the equation they gave me. I'm saying that becomes 0 because it hits the ground. So essentially that's what I'm solving here. That gives me two possibilities for t. Now one of them I can discount straight away because it's obvious. T equals 0, well yeah, because I projected it from the ground. Of course I get an answer of t equals 0 as a possibility. It must be the other one that I'm looking at. So alright, it will hit the target after 4u sine theta over g. Now when that happens, what is the horizontal displacement of my projectile? So we'll sub it into that expression that they gave me. And we end up with 8 sine theta cos theta, which I've changed to 4 sine 2 theta. Now I can easily explain why maximum range occurs at 45 degrees, because that would become sine of 90, and the sine of 90 is 1, the maximum of the trig curve. Okay, so I can look at that and I know, right, its maximum range will be 4u squared on g. That's important because you remember in the question it said some percentage of the maximum range or so, wasn't it worded like that? So we need to know what the maximum range is. Okay, now, yeah, don't set yours out like this. I just did it so it fits on one slide. I've now gone and worked out the horizontal position of the target, because remember the target is moving. So sub in 4u sine theta on g into that, and we get d plus 4u squared sine theta on g. Now, in order to hit the target, the displacement of the target must be less than or equal to the displacement of the projectile. Because if it lands before the target, then clearly it can't hit the target, it's further away. So d plus 4u squared sine theta over g must be less than or equal to 4u squared sine 2 theta on g. Okay, playing around with this equation, I get 4u squared. So I now know what the distance has to be less than or equal to. Okay, now d therefore will be maximised. So the biggest of that inequality, remember u is constant, g is constant, it will be when this expression here, sine 2 theta minus sine theta, when that is at a maximum. That's going to give us our biggest possible d. Let's call that function theta, sine 2 theta minus sine theta. Differentiate that because I want to maximise it. 2 cos 2 theta minus cos theta. Playing around with the trig, I end up with a quadratic here. 4 cos squared theta minus cos theta minus 2. Stationary points, because that's essentially what I'm trying to find, I want to maximise this, will occur when that derivative is equal to 0. Cos theta is 1 plus or minus the square root of 33 on 8. But hang on, I'm projecting it. I know theta has to be acute. Because if it was obtuse, I'm firing behind me, that would be stupid. Negative, I'm in the ground. No, got to be acute. So it must be the 1 plus root 33 on 8 answer that I'm looking for. Yeah, it's approximately 0.8431. Okay, but I need to know sine theta as well to plug it back in. So a little bit of work there, remember? Sine squared equals 1 minus cos squared. So yeah, roughly 0.5378. Let's go back to d, see what happens. Sub those numbers in. Again, I'm doing approximation. I'll take it at 4 decimal places. It should be okay. 4u squared on g times 0.3690. Okay. Well, hang on a sec. Remember 4u squared on g? That's what we said maximum range was. So that is about 37% of the maximum range, and that is what I had to show. A lot of work for that question. All right, so 10A.